Hi, everyone. It's time for a little general chemistry, but we're going to actually do some organic chemistry. So we're nearing the end of Chem 26, second semester of general chemistry, and it's time to preview the next level of chemistry, and that's organic chemistry. So let's look at some PowerPoint slides. Your original set of PowerPoint slides have been shortened by me. Silly. But anyways, I put the original set of PowerPoint slides on the Canvas website in case you want to see what the whole shebang's all about. But in terms of what will be potentially on the final exam, I've reduced the content to these slides here. Okay, so what is organic chemistry? Organic chemistry is the study of carbons. We're totally focused on the sixth element on the periodic table. And many of the molecules consist of just hydrogen and carbon. So a good name for that collection of molecules is hydrocarbons. More specifically, if all the bonds are single bonds, those hydrocarbons are called alkanes. So alkanes are just hydrocarbons, molecules with C's and H's, carbon, hydrogen, and only single bonds. And then we have a saturated hydrocarbon. Okay, so like if you dip a rag into a bucket of water, squeeze it out underwater, and then just gently lift it up, and so it's dripping wet, it's got the maximum amount of water on that rag, it's saturated. We can say hydrocarbons can be saturated too if they possess the greatest number of hydrogen atoms, right? So carbon bonds 4 times, and if all the bonds are single bonds, you can actually obtain the maximum number of hydrogens that way. But if there's some double bonds in the molecule or triple bonds or rings, right? So if you take a long chain of carbons, connect them end to end to get a ring, then those are not going to be saturated with hydrogen. Double bonds, triple bonds, rings take up some bonds that could have been attached to hydrogen. Anyways, another useful term we'll see later, saturated hydrocarbons. Ooh, okay. So here's the first big idea is that these molecules have a lot of carbon in them, right? Organic chemistry is a study of carbon. So we start to get a little lazy and we simplify our drawings. So what we have on the screen is something that you might begin by drawing. As a beginning organic chemist, you might want to represent all the C's, all the H's. Tell the reader exactly which element is at which bond. And then as you do more chemistry, you realize, man, that takes a long time to draw all those C's, H's, and all those lines. So let's shorten it up. Here's the same exact molecule in a condensed formula. So that's where you stop drawing the bonds to the H's. So over here is represented like this. Same thing, just a shortcut. And then when you get really tired, it's like, ugh, I'm not even putting my H's or C's in there. All we're going to do is draw the bonds. So we got this bond here and that bond there. That's this one and that one. Anyway, it takes some getting used to. That's just like the bare bones, the skeleton part of the structure, the skeletal drawing. Essentially what you need to do is when you see these types of drawings, skeletal drawings, is that every end of the bond is a carbon, every intersection of bond is a carbon, and every bend, so this is a bend here, that's a bend there, there's the end of a bond, they all represent carbons. And then keep remembering the shortcut, HONC, 1, 2, 3, 4. The H stands for hydrogen, but it also stands for halides. Hydrogen and halides prefer 1 bond. O stands for oxygen, prefers 2. Nitrogen prefers 3 bonds, but carbon prefers 4. So knowing carbon wants 4 bonds and we only see 1 bond to this carbon, that tells us there must be 3 more for a total of 4 bonds to the C. And then if you wanted to, you could then expand it to see all the bonds. So this line drawing, that's another name for a skeletal drawing, is very helpful. It's a shortcut way of drawing complicated molecules fairly quickly, but it does take some time to get used to it. So give yourself some practice. get some time to get used to that, because if you take organic chemistry next semester or next year, whenever it's in your schedule, if it's in your schedule, you'll be doing line drawings, skeletal drawings all the time. So you'll see a couple of these on the final. I want you to break it down, or I might ask you to take, hey, the full structural drawing, expanded formula, and draw it as a skeletal drawing. Okay. Yeah, stop that. You can advance. There we go. When we talked about transition metals, we talked about isomers. The organic chemistry is full of isomers. Isomers are different molecules, but they have the same chemical formula. Okay, so compare that to other situations. If molecules don't have the same chemical formula, they're definitely different molecules, right? But here we got molecules that still are different, but they possess the same chemical formula. And all we're doing is saying, hey, let's just attach them differently. So as an example, right down here, we have a chain of 4 carbons in a row, and we have a chain of 3 carbons, and the 4th one branches off the middle carbon. I hope you see that these are clearly different molecules. In fact, if you go and measure the boiling points, the melting points, they're different. They're different molecules. Okay, and if they're different molecules, they should have different names. They do down here at the bottom, but they actually still have the same chemical formula. There's 4 carbons and 10 hydrogens in both. Same chemical formula, different molecules. That makes them isomers. Constitutional isomers, I won't be testing you on that, but constitutional isomer just says, hey, you're breaking these bonds and reconnecting them in a different way, right? So 4 carbons in a row versus 3 carbons in a row with 1 branch. That's a constitutional isomer. We'll see geometric isomers in a little bit later in these slides. We saw those for transition metals, right? Cis and trans. We'll see them here too. Ooh, so a little test, right? So are these isomers, are the same compound, or maybe they're just plain different? Well, what are the chemical formulas? We got 4 carbons, and there's 3, 5, there's 10 hydrogens. There's 4 carbons here, and there's 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's the same formula. 4 carbons, 3, 5, 10. Okay, they all have the same chemical formula. So they could be isomers, or in fact, they could be just the same molecule bent into a new shape, right? So if you ever play with molecular models, single bonds are free to spin and rotate. So molecules are not just hard and fast molecules. No, they can bend and flex and twist, assume different shapes, yet they can still be the same molecule in a new shape. So one way to see whether these are actually different molecules, like on the previous slide, whoops, gotta get out of here. Let's go on the previous slide. Please go back. There it goes. Okay, so we had 4 carbons in a row, right? So let's circle that. 4 carbons in a row. That is different from 3 in a row with 1 carbon branching off. Maybe we'll do that in red or something. Okay, there's still 4 carbons, C4H10, but the arrangement, the connections are different. Yeah. Or another way to think about it, we could draw this molecule like this. And I'll use a condensed formula. Skeletal drawings right up there. Okay, these two are the same molecule. How do you know? It's still 4 carbons in a row. I've just bent the chain, right? So there's 4 C's here, but here's 4 Z's. 4 C's zigzagging, 4 carbons zigzagging. Doesn't matter if it's bent, zigzagging, whatever. This is the same 2 molecules. These are the same. Just bent into a new shape. But there's no way to bend or twist to make this a chain of 4 in a row. No, and there's no way to bend or twist this to make it in a chain of 3 with 1 branch. The only way you could do that is physically break a bond and then reconnect this to this end. And if you're breaking bonds, you might be making a new molecule. Okay, so these are different. There we go. Okay, so let's see if these are the same or different. So why don't we just circle the carbons? So we'll start here and just circle the carbons. There are 4 carbons in a row. It's kind of bent around. Here's 4 carbons in a row. Hey, these are the same. The same. It's just twisted in different shape, but it's still 4 in a row. 4 in a row. And in fact, here, they're all the same. Sorry, that's supposed to be a double-headed arrow. All 3 of these are the exact same molecule, just twisted into different forms. They're all the same. Oh, gotta erase the screen. There we go. Okay, number 2, the following condensed structures have the same chemical formula, C8, H18. Which of them represent the same molecule? Well, let's use the same strategy. Let's circle the chain. So, but we have some branches. It may be a little tricky sometimes. You might have to start on a branch. I don't think you have to here. Let's just go along the horizontal portion of the molecule. And then let's number them. How many carbons are here? I'm putting numbers by them. I'll start on the left here, and there's 1 carbon, 2, 3, 4, 5, and 6. And the 4th carbon of what I circled, this carbon here, has a branch, a 1 carbon branch. And then off the 2nd carbon of my chain that I circled, here's 2nd carbon, there's also a methyl, there's also a CH3, a carbon out there. All right, let's do that again. Got a chain here. And if I start numbering from this end, 1, 2, 3, then it looks different. But what if I number from this end? 1, 2, hey, 2nd carbon's got a branch. 3, 4, hey, 4th carbon has a branch. 5, 6, these 2 are the same. Turns out one of the rules is not a rule, it's a non-rule. There are no rules, no regulated, agreed upon method on how do you want to draw a molecule. Sky's the limit. You could draw these however you want. Someone decided to draw them horizontally, 6 in a row with the branches pointing up, but you could draw them vertically. I got 6 yet? And then you can put branches, 1 on one side, the other one on the other side, and fill this all in with H's. Try and get to my formula. All this to make a point. Whoa, okay. Press the wrong button there. Probably lost all my slides too, all my graphics. Yep. All right. But the main idea is, it doesn't matter how you draw it. Sorry about that. Doesn't matter how you draw it, as long as we saw 1, 2, 3, 4, 5, 6 carbons in a row, and it could be a zigzag, could be a bent, it could be bent into different shapes. As long as there's 6 in a row, and off of the 2nd carbon, there's an extra branch, and off the 4th carbon, there's an extra branch. They're the same. All right, so let's check this last one. Circle this. We got 1, 2, good. 2nd one has a branch. 3, 4. No, we're missing something. This is different. Here's 5 and 6. Yeah. If you renumber it and go, well, let's say this is 1, then 2. Yep, we got a match. And then we got 3, 4. Whoops. 4th one doesn't have a branch. These are different. Not the same. Yeah. Cool. All right. Let's get rid of that so I can forward to the next slide. Maybe. There we go. Ooh, draw all structural isomers of pentane. So pentane sounds like pentagon or penta. Remember we used penta when we're naming molecules. Penta means 5. So this is a hydrocarbon, C5H12, just C's and H's. And it has a, sorry, I'm glitching here on the screen. It's bugging me. Okay, I think we're okay. Hope it's recording. C5, pentane, 5 carbons. That's what we're going for. Okay, but it wants isomers. So we want a whole bunch of different molecules, but they're different molecules. They all have the same chemical formula. That's what an isomer is. Same formula, different molecules. Well, let's go back. Let's give me the screen here. There we go. If you're not used to skeletal drawings, maybe I should draw it out. How about if I use a condensed formula? Okay, these two are the same molecules. It's 5 carbons in a row. You could also have 4 carbons and have a branch. So 4 carbons, and then we have a branch. And then honk, keep remembering honk. 1, 2, 3, 4. All my carbons have to be making 4 bonds. So I'm doing this pretty quickly because I have a lot of practice. But this carbon right here is this carbon right here. And there's a carbon up above. Yep. Carbon to its left. Yep, this one. And this carbon's making 1 bond up, 1 bond to the left. There's a hydrogen it's connected to. If you want to, you can draw it in here. And then this carbon's also connected to the next carbon of the chain. This carbon is this carbon. 2 H's that are not being drawn in, and 2 carbons. Yep, 2 H's and 2 carbons. Anyways, supposed to be drawing all the isomers. So I got 5 in a row. 5 in a row. That's the number 5. No branches. Now I did 4 in a row with 1 branch. You might want to move the branch. So you might say, let's have 4 in a row and then put a branch here. Wait. 1, 2, 3, 4 in a row. 1, 2, 3, 4 in a row. The second carbon's got the branch. Yeah, the second carbon's got the branch. These are the same, so I'm not going to draw it again. It's not different. Yeah, I can't. If I put the branch at the end of the chain, so I got 4 in a row and a branch at the end. Wait, that's not a branch. That's 5 in a row. Okay, we've found all the possible ways of getting 4 carbons a row with 1 branch. All right, but we can do 3 in a row. 3 in a row, and then we can put 2 branches on. Yeah, so 3 in a row. That's just a central carbon with CH3s coming off of it. I feel like I'm forgetting something. That might be it. Is that really it? 3 in a row, 2 branches. Yeah, I can't move these branches anywhere else. That's it. Weird. You know, one of the things that we don't have is a way to predict the number of isomers given a formula. I wonder if anyone's found a way to figure that out. It's really just done by trial and error. So on the exam, I'm not going to ask you for all. I might say, hey, give me 2, or maybe give me 3, and I'll make sure there are at least 3 possible ones, right? So it's a little difficult to make sure you got them all because there's not a good way of checking other than by just trial and error. I still feel like I'm missing one. Hopefully not. Okay, enough of that. Next slide, please. Naming. Okay, so there's a little bit of naming of organic molecules on the final. It actually builds off of stuff you already know. So if you look at the list here, and you got pentane, that's 5 carbons. Oops, keep forgetting to turn on the pen. Go back, please. Give me the pen. Okay, so we know pent means 5 carbons, so pentane is a molecule with 5 in a row. Hexane is 6 carbons in a row. Heptane, like the heptathlon in the Olympics, the women's event, was 7 events. That's a heptathlon. An octopus, 8 octane. Nonane sounds like 9. That's all I got. And a decade has 10 years. So decane has 10 carbons in a row. Now, unfortunately, when we're naming, before we use mono, di, tri, and tetra, then the penta and the hexa. So sadly, for organic chemistry, we don't use those. We use methane, ethane, propane, and butane. And so a student told me, just remember Molly eats peanut butter. Or Mark eats peanut butter, or Mabel eats peanut butter. And then now you got the M, the E, the P, and the B, methane, ethane, propane, butane. And in fact, butane actually sounds like butter, B-U-T, that's kind of nice. And after that, it's the normal prefixes that hopefully you still remember from nomenclature, naming molecules from before. Maybe we should talk a little bit about what we're saying up here. So IUPAC is the International Union of Pure and Applied Chemists. So there's an international committee. They actually still meet, and they just talk about how to name organic molecules. You see, there's organic molecules studied around the world. Someone discovers something new and want to be able to name it. And there's a committee that's regulating the names. So let's just make sure all these names are systematic. There's a procedure. Sometimes the procedure has some problems. They work them out in committee. We got a set of rules and guidelines on how to name molecules. So here's the guideline. If you see a name of organic molecules, somewhere in the name, it'll tell you how many carbons are present in the longest row. And unfortunately, it's not always longest row. The committee made some changes. But anyways, there'll be a sequence of carbons. So if you read this name, an organic name, and somewhere in there you see heptane, hept means 7. So the molecule is going to have 7 carbons in a row. And then in front of heptane, there'll be some other prefixes telling you what else is attached. Like what other decorations are attached to this chain of 7 carbons that we call heptane. And at the end, there'll be another suffix where heptane just means alkane, carbon-carbon single bonds. You might have other organic molecules with a double bond in it, a triple bond, in which case the suffix, the ending will change to reflect that there's not only a single bond in there, there's some other, there's a double bond in there, or maybe a triple bond, or maybe there's other elements present. Maybe oxygen or nitrogen, maybe some double bonds to oxygen. Okay, so the suffix is going to tell you something else about the molecule. More on that in a minute or two. For now, you do need to know the first 10 alkanes. And here they are, all hydrocarbons, all saturated. They got the maximum number of hydrogens. They're also not branched. They're all straight chain. So methane, ethane, propane, butane. Molly eats peanut butter. Pentane, hexane, heptane, octane, nonane, decane. Gotta get those memorized so you can figure out what a molecule looks like from the name, or if I draw it, can you name it? That'll be the objective, at least one problem on the final. Okay. There we go. Oh, here's a set of steps, a procedure for naming. So if you have a structure and you're asked to name it, when you take more organic chemistry, we're going to change these rules a little bit, but this will help you in the beginning. We're going to name the parent chain. And in this case, for these examples, you're finding the longest chain. So longest set of carbons in a row. Don't be deceived by the way they draw it. So if someone drew it with one, hey, where's my pen? There's 1, 2, 3, 4, 5 carbons drawn horizontally here. And then there's a branch point with 2 more carbons. But it turns out you can start here and get more than 5 in a row. You can actually get 6 in a row. So the longest chain, even if it's bent, twisted, whatever, find the longest sequence of carbons in a row. That's step 1, finding the parent. That'll help you construct the name of this molecule. Okay, and then if you have a chain, there's a beginning to the chain and an end to the chain. You need to pick the end that gets you to the first branch or the first decoration, another double bond or a triple bond or another element. It's important to count from the end of the chain that gets you to something interesting as fast as you can. So we got a chain of 6 carbons here, and you have a choice. Is the carbon on the left side of the chain the first one, or is the carbon on the right the first one? And the answer is the chain begins on the side that will get you to the branch point as fast as you can. So in this case, you have to number it 1, 2, 3. On carbon 3, you get a branch, and not over here with a 1, then a 2, a 3, and then 4. No, it's taking too long. IUPAC, the International Committee of Pure and Applied Chemists, said you must, everybody, no matter how you draw it, everyone gets free liberty on how to draw it. But after it's drawn, you have to number it from the end of the chain that gets you to the first branch as fast as you can. Okay, so we found the parent, the longest chain. We numbered it, and now as you go down the parent, you need to identify those branches and name them. And you also have to give a little number to say, hey, where off the parent are they branching from? So we got a chain of 6 here, and the name of that is hexane, one of the 10 alkanes. Off of carbon 3, there's one more carbon. Now, I don't have it on here, so it must be on the next slide. We need a name for this 1 carbon group. Now, if you had a parent chain of 1 carbon, that's methane. You know, Molly eats peanut butter. But this 1 carbon group's not the parent, it's a branch. So instead of methane, we're going to call it methyl. That's coming up on the next slide. Here's another example. We got a chain of 6. And let's move this out of the way. Put up here. We got a chain of 6, and off of carbon 3, on the bottom, there's a 1 carbon branch. Also on carbon 3, there's a 2 carbon branch. So we need to name those branches, and we'll use prefixes. We'll put them in front of the name, hexane. Why is it advancing? There we go. Okay, and here's how we're going to name those branches. Molly eats peanut butter, so here's methane for Molly, and here's eats as ethane. If you want it to be a branch, then you have to remove a hydrogen and connect that group using this bond connected to the parent. This is our 1 carbon branch, no longer called methane, it's called a methyl, YL ending, meaning kind of less important. It's a branch, not the parent, not the longest chain. Ethane, do the same thing. Drop the ane and add YL, an ethyl group. Okay, so again, you have to memorize the first 10 alkanes, knowing Molly eats peanut butter, methane, ethane, propane, butane, and then pentane and so forth. They'll also allow you to name the branches by changing the names, methane, ethane, propane, butane, to methyl, ethyl, propyl, and butyl. Here's some examples. Propyl, butane becomes butyl. Okay, so on the exam, We won't do isomers of these chains, but they exist. You don't have to worry about isopropyl, stacbutyl, and all that stuff. Not until you take the full-blown one-year course of organic chemistry. Still going through the procedure on how to construct a name. You're just jamming all these prefixes, parents, and suffixes together. The grammar or punctuation, as I call it, is you want to use dashes or hyphens anytime you're separating a number from a letter. Use commas to separate two numbers. And if you have letters, just jam it all together. If you have more than one branch, you list them in alphabetical order. I think we did that with transition metals complexes, so that's nice. Oh, if two or more identical groups are present, use one of the Greek prefixes, di, tri, tetra, so forth. Yeah. Okay. Let me check the next slide. This says identify substituents, so maybe we just want to name the branches. And then we can name the whole thing. All right, so let's go back and name the whole thing. Let's just do this. Okay. Let's name these. So what you want to do is first find the longest chain. Technically, you have to find all the potential ends. Like this is one end of a chain maybe. And you might say, well, is it a chain of 5 in a row? Or is it a chain of 4 in a row? Or is it a chain of 6 in a row? Well, the longest chain wins. So this is the parent. I like circling the parent. It helps. That's the longest chain, a chain of 6. And then Molly eats peanut butter. Pentane, 6 is hexane. The parent name for 6 in a row is hexane. They've already numbered it for us. Why did they go 1, 2, 3 and not 1, 2, 3, 4? They wanted to get to the branch as fast as they could. So the correct numbering is 1, 2, 3. Got to this branch. What's the name of that branch? It's a 1-carbon branch, so it's Molly. No. It's methane if it was a parent, but the parent's hexane. So only hexane gets to keep the ane ending. You cross that off and you add YL. So methane, lose the ane and add YL. And off of carbon 3 is the methyl group. So then the name is 3-methyl hexane. So separate the number from a letter with a dash or hyphen. Methyl and hexane doesn't get separated, just cram it all together. Okay, and then do it again. We got a chain 1, 2, 3, 4, 5, 6, or 1 through 6. Turns out we're going to get the same name whether we go straight horizontally or we say, hey, let's take the 6 right here. It's kind of interesting. Well, they already numbered the vertical, the horizontal one. So let's just call these the parent. It's a chain of 6, which is hexane again. Numbered it from this end to get to the branches as fast as you can. Not from this end, 1, 2, 3, 4. Nope. From the left side again, 1, 2, 3. This we know from up above is a methyl group coming off of carbon 3. There's also a 2-carbon group. That's eats. Molly eats peanut butter. Eat reminds me that the 2-carbon group is called ethane, but that's a parent name and that's a branch. So lose the ane and add YL. And on carbon 3 is a branching ethyl group. So there's a 3-ethyl and a 3-methyl. Put them in alphabetical order. So E first. And then methyl after ethyl, alphabetical order. And again, separating numbers from letters with a dash or hyphen. Number from a letter with a dash, number from a letter with a dash. And then I got methyl going to be smashed right up against hexane. And there's your name. Here's my parent. We saw this in an earlier slide. Chain of 6. And it doesn't always have to be straight. No rule about that. Draw it however you like. 6 in a row is still called hexane, no matter how it's drawn. Zigzaggy, straight across, whatever. Off of carbon 3 are 2 methyls. So this one is a methyl off of 3. This one is another methyl off of 3. Okay, we have the same group showing up twice. It's not so important that it showed up on the same number. It didn't have to. It could have been, a branch of methyl off of 4 and 3. But there are 2 branches that are both methyl. So in the name, you're not going to say 3-methyl hexane. That sounds ambiguous and then redundant and too long. If the same group shows up more than once, you only say that group methyl one time, and you throw another prefix in front to say how many times it showed up. Well, it shows up twice, so that's di. So we're going to say dimethyl. Well, and then we're going to put the parent name next, hexane. Cool, dimethylhexane means chain of 6 and there's 2 methyl branches, but where? Okay, so you have to keep the 3s. If you have di, then you need 2 numbers. It's not assumed that they're both off of the same number. They don't have to be, right? You could have had a methyl group off of 2 and 3, or 2 and 4, or 2 and 5, or 4 and 4, 5 and, yeah, it could be 4 and, well, it can't be 4 and 5, but 3 and 4. If it was 4 and 5, we'd renumber the chain so we could get to a branch faster. Yeah. So give me the eraser. Should be underlined. There we go. There's the name. 3,3-dimethylhexane. 2 methyls, you have to say the location of each of those. And we'll separate numbers from numbers using a comma. Number from number, comma, number from letter, dash, letter to letter, who cares? Smash it all together. Ooh, another hydrocarbon to name. Okay, let's find the longest chain. Well, you could start here. Where's my, darn it. Still not used to it. I think by now I would be. Okay, you can start here, or here, or here. There's 3 ends. So if we go from this end to that end, there looks like there's 8 in a row. If you start here and go down here, there's only 7 in a row that way. If you start here and go that way, that's 8. Ooh, so you can either go straight across for 8 or down here for 8. Turns out it's going to be the same either way. The branch point here can either have 3 carbons this way or 3 that way. And that's how I recognize weight. It doesn't matter. So why don't we take the easier route? Let's go straight across. You didn't have to. If you just said, hey, my longest chain's right here, it's a tie. It's chain of 8, chain of 8. We're going to get the same name no matter how we name it. I mean, so whichever parent name we call it. Okay, so I'll go 8 across. And then let's number the parent. Do we number on the left? We've always been numbered on the left, right? No. If you do, it'd be 1, 2, 3, 4, 5, branching off of 5. It's better, and actually it's correct, to number it from the right side this time. So the branch comes off of number 4. What's off of number 4? A 3-carbon branch. That's peanut. Molly eats peanut butter. That reminds me of propane. Sorry. 3 carbons is propane, but lose the ane ending. Propane is the name of a 3-carbon for the longest chain, the parent. This is a branch. This is a propyl branch. 8 carbons, octopus has 8, so this is octane. Yeah, that's the same word that you see at the gas pumps. I think that's in the slide coming up. Or maybe it's in the homework, I forget where. Gasoline. It's full of hydrocarbons. Okay, let's finish naming this. Got the parent, got the branch. There's only one branch. It's coming off of carbon number 4. So on carbon 4 of the parent, there's a propyl group attached to the parent name octane. 4 propyl octane is the name of that molecule. Okay, so we're gonna have to change this one. Remember earlier I said I'm not going to put isopropyl or isobutyl, terbutyl, all those. So let's take that out. Okay, so maybe I would ask you to draw 3-propyl 2-methylhexane. Okay, I suggest working backwards. Instead of going with 3-propyl, start with hexane. And when you draw it, you decide how you want to draw it. If you're comfortable with skeletal drawings, use that. Condensed, or if you're like, nope, I need to draw all the C's, all the H's, I'm doing a full structural drawing, any method works for me. So maybe we're getting some practice doing this. Why don't we do both? We'll start with the full-blown structure. So draw all your C's and H's with all the bonds if you wish. Hexane means 6 in a row. Or you could go skeletal. 1, 2, 3, 4, 5, 6. It's important to zigzag, right? Because if you just drew a straight line, it's like, how do you know how many carbons are there? So if you're drawing the C's and H's, you could go straight chain, straight and linear. But if you're doing skeletal drawings, you have to zigzag so it's clear to the onlooker. It's like, how many carbons are here? Yeah, at every bend, there's a carbon. Oh, is the real molecule straight like this? Are the bond angles 90 degrees like it looks like here? I mean, if you, let's see, anything off the 2 there is. If you wanted to draw on the H's, are they 90? No, these molecules are 3-dimensional. Let's get rid of that. This is skeletal drawing. 4 bonds needs 4 orbitals. So this carbon needs an orbital for this bond, this bond, this bond, this bond. That's 4 orbitals. It needs an S, a P, and a P, 4 orbitals. This is sp3, which you should know is tetrahedral. Okay, so actually the skeletal drawing is a little more accurate. Tetrahedral carbons would actually zigzag. They're not going to be flat like this. Anyways, when we draw the structures, we don't necessarily are drawing their true shapes. We just want to see how the atoms are connecting together. 6 carbons in a row. And then after you got 6 carbons on the row, I can't kind of work backwards. So there's a 1-carbon branch, methyl, moly, and it's coming off of carbon 2. So when you're drawing, you decide how you want to number it and how to draw it. So I put 6 carbons in a row. I'm going to number from the left. This is carbon 2, and you want to put the 1-carbon group above or below. They both work. Here's my 1-carbon branch. And then honk reminds me that carbon must have 4 bonds. And then the rule, it's kind of a rule, if you decide to draw C's, you must draw H's, right? So if you said, oh, let's do the branch off of carbon 3. Here's carbon 3. There's a propyl group, so that's 3 more carbons. So 1, 2, 3. If you said, there you go, Dennis, there's my molecule, I'll say, no. If you want to omit the H's, you have to go draw skeletal. If you're drawing the C's, you're compelled to draw H's. So remember honk and put in the H's. This C has 4 bonds. This one has 3 bonds. So there's 1 more H. This C only has 1 bond. You could draw all the bonds. I will allow you to mix it though. If you want to draw this as a condense, now you have your C's and H's. Here's your H with a bond. Here's your H without. Your choice. They both work. You can squeeze this here. That's a neat trick. Student showed me that. Just change your bond to the, yeah. So this carbon is bonding over here to this carbon, but it's also its 4th bond is to this hydrogen. And then these are CH2s. This one's a CH3. And then now everyone's making 4 bonds, except for this one. That doesn't look right. I think this needs 2, this one needs 2, and this one needs 3. So full structural, condense, I will allow you to mix and match, but the bottom line is if you're drawing C's, you must draw H's. If you go skeletal, then you can leave out the C's and H's, but only if it's skeletal. Wait, this isn't the right molecule, this is hexane. Alpha carbon 2 is a 1-carbon branch. I don't like drawing it down here because that makes the bond angle really tiny. What's the bond angle on sp3 hybridized atoms? It's approximately 109.5. And if I drew it down here, that looks like about 45 or 30. That ain't right. So it's better to draw it up here. So then the bond angle looks like 120. I know that's, at least it's closer to 109.5. It's not the true drawing. But that's a 1-carbon branch. And then off of 3, there's a propyl branch, 1, 2, 3 carbons, and then link it to the parent. And that way you still have 1, 2, 3 carbons on the branch. There you go, skeletal drawing, structural drawing here, full structural drawing. And you'll notice the the propyl group, 3 carbon chains up. Here it's down, doesn't matter. These are the same molecules. You can draw them however you want. If you had the molecular model, you could take this, build it, and flip it upside down and bend it and make it look like this. You can get it into that shape. They are the same molecules. Hence, you can draw them lots of different ways. All right, what else we got? Okay. Let's look at some other possibilities. We've been dealing with only carbon and hydrogen, and only single bonds between the carbons and the hydrogens. Well, hydrogen can only make 1 bond, so it will always be single bonded. Carbon can make 4 bonds. So now we have some variations. Single bonds between carbons, double bonds or triple bonds. No quadruple bond, nope. Haven't seen that in nature yet. And then we have names for those situations. So we had alkane. The alkane was all single bonds. An alkene, so we're changing the ane ending to an ene ending, it contains at least 1 carbon-carbon double bond. An alkyne, Y ending, has to be a hydrocarbon with at least 1 triple bond between carbons. Oh, and once you double up a bond or triple up a bond, you need to take away some hydrogens to make room for the double bond and triple bond. So now that it's not saturated with the maximum number of hydrogens, it's not saturated, so it's unsaturated. Did you notice that this is in alphabetic order? Alkane, alkene, alkyne, single, double, triple. That's handy. That'll help us remember the names of those types of molecules. So a molecule with at least 1 carbon-carbon double bond is called an alkene. At least 1 triple bond is alkyne. I know someone's thinking, what if it has both? We'll get to that next semester if you take organic chemistry. But actually in the name, you'll see both ene and yne if a molecule has both a double bond and a triple bond between carbons. Not this semester, I won't show that to you. So how do you name molecules with double bonds in them? Well, you still use Molly Eats Peanut Butter, methane, ethane, propane, butane, but you change the ane ending to an ene. So 2 carbons used to be ethane, but now it's double bonded, so it's ethene. Propane, 3 carbons all single, but propene, 3 carbons with at least 1 double bond. Butane becomes butene. And once you get the 4 carbons or more, then it's not obvious where the double bond is. Some of you might be saying, well, couldn't the double bond be on the right side? Couldn't you have done it this way? And the answer is yes, but you've got a number from the end that gets you to the branch or the interesting feature as fast as you can. So over here, this is going to be carbon 1, 2, 3. And over here, you want to get to that double bond as fast as you can. Now this is 1, 2, 3. So there's only one way to put a double bond into a 3-carbon chain, because you'll always be numbering it from the end that has that double bond. But now you have 4 carbons. You can either have the double bond at the ends, and it'll still be 1, or you can have the double bond in the middle. Those are isomers. They have the same chemical formula, but they're different molecules. Double bond at the end, double bond in the middle. That's different. So they must have different names. And so just like we identified the branch point, we'll identify the start point of the double bond. So in butene, ene says there's a carbon-carbon double bond in a chain of 4 carbons. And this says where, sorry, I missed. This one says where the double bond starts. Starts on 1. And ene means double bonded. So you start on 1, that implies the second carbon. The one right after that must finish the double bond. 2-butene says, yes, start the double bond on 2 and end it on 3. Cool. What we got here? Isomers. 5-methyl-2-hexene, 2-methyl-3. Oh, do you see how the methyl, the 1-carbon branch, is on a high number? And over here's on a low number. So what's going on? Turns out that the double bond is part of the suffix, and the methyl is a prefix. And turns out the suffix is more important. So when you're numbering this, remember what we said, you have to number from the end to get you to a branch or to an interesting feature as fast as you can. IUPAC, the committee who decided on how to name molecules, said, let's prioritize. If you have more than one feature, number it according to the suffix. So if you had to look at this molecule and say, okay, how do I name this? You'd say, okay, find the parent. 1, 2, 3, 4, 5, 6, and not 3 in a row. I guess you could say 6 in a row this way. Let's just go horizontally. It's going to get the same name. Found the longest chain here. Then number it from the end that gets you faster to the suffix portion. Not necessarily the 1-carbon branch, because that's a prefix, methyl, but the suffix ene of hexene, right? It was 6 carbons, which was hexane, but the double bond means change the suffix ane to ene. It's now hexene, and the suffix is the priority. So which side should we number from that can get us to that double bond as fast as possible? As drawn here, should be on the left side. 1, 2, on carbon 2 is going to begin the double bond. So we're going to number it this way, and after we set the numbering based on the double bond, wow, I didn't know I could do that. Based on the suffix ene, then just see where the methyl group end up. It ended up on number 5. So it's now 5-methyl-2-hexene. Do the same thing here. We kind of numbered from the left side, we got to the double bond on carbon 3. If you number from the right side, you can also get the double bond on number 3. It's a tie. How do you break the tie? Well, in this case, it's the most important group, the ene group suffix, can get 3 either way. Well, then let's break the tie by choosing the one, the numbering, so that we can also get to the branch quickly too. And so that's why they chose to number from the right side, because the methyl group was a tiebreaker. Coming in from this side, we can reach on carbon 2. Yeah. So 2-methyl, that's the branch point, prefix out in front. Hexene's the parent, but change the ane to ene and identify where it is. 3-hexene. The ene begins on carbon 3. One little bit of information about carbon-carbon double bonds is that they don't rotate. A double bond can't spin. Only the single bonds spin. Technically, a triple bond doesn't spin either. But we don't run into the same problem that we do on double bonds. Carbon bonds 4 times. So if you look at this carbon right here, but it's just so sensitive. Look at this carbon right here, it's making a double bond and it has 2 more bonds. And the hydrogen is on the bottom part, the lower half of the double bond. And on the other carbon of the double bond, there's a methyl group up above and another hydrogen. The 2 hydrogens, the 2 identical groups, are on the same side. You could say the 2 identical methyl groups are on the same side above. And that's a different molecule than when the methyls are across a double bond or the hydrogens are located across a double bond. The double bond can't spin. If it could spin, it could just switch back and forth. But they're not single bonds that can spin and bend and flex. These are different molecules. They're isomers, but it's a different type of isomer. It's not a constitutional isomer. It's still 4 carbons in a row. 4 carbons in a row. No, it's because the double bond locks the shape in place. It doesn't allow it to spin. Now it matters. Hydrogens together, hydrogens apart. And so we need a new name, a new prefix to differentiate, to tell the difference between these 2 molecules. So the prefix cis and trans are used, and you've already seen it in the transition metal complexes. But the way I remember it is we use the prefix cis, which has a soft C. It looks like cis, like in sister. And then I remember the 2 S's mean same side. So when the identical groups, 2 methyls or the 2 hydrogens, the identical groups are on the same side, you use a cis out in front. This is 4 carbons in a row, butane, but there's a double bond, so it's butene. Where does the double bond begin? Well, 1, 2, 3, 4, or you could do 1, 2, 3. Either way, the double bond begins on number 2, 2-butene. Ooh, but which variation is it? Hydrogens together, hydrogens apart. They're together, same side. So then it's cis, 2-butene. Transamerica, transcontinental. Trans means across. Transfer, get things one side to the other. Yeah, then you have that prefix. If the identical groups are across the double bond. Trans 2-butene down there. Oh, so let's draw something. We'll use both the skeletal drawing as well as a full structural drawing. So I start the right side, read backwards, heptene. So heptane has 7 carbons. 1, 2, 3, 4, 5, 6, 7. Or you could zigzag it. Let's see, 1, 2, 3, 4, 5, 6, 7. And then on carbon 3, now since I'm drawing it, I get to decide which end to start numbering from. I'm a number from the left side. So on carbon 3 begins a double bond. On carbon 1, 2, 3 begins a double bond. And then it's supposed to be cis. So that means the identical groups, the hydrogens, should be above on the same side. Oh, they both could be below. Now, sadly, if you're drawing skeletal, remember, this is, you know, I don't want to draw a hydrogen down here. It gets too crowded. The hydrogens should be up and down here. This is actually trans, because my double bond runs like this, and the identical hydrogens are across the double bond. Oops, that's not right. So why don't we draw a double bond? And this will be carbon 3. So I need 2 more carbons. So 1, 2. So starting over, this is carbon 1, 2, and then 3. This is 4. And then I gotta go 5, 6, 7. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. Good. And then this is cis. It's understood that, well, you can see that this carbon, part of the chain are above the double bond, which means the two hydrogens must be below. Why? What's the hybridization of this carbon? And if you don't like skeletal, let's go over here. What's the hybridization of this carbon? Well, this carbon has two singles and a double. And for hybridization, the double and triple bonds count as one group. So this carbon has three groups, each requiring an orbital. And these an S, a P, and a P. This is sp2. To be technical, one of these is the sigma bond. That's being used, that's using the sp2 hybridized orbital to make the sigma bond. The other one's going to be a pi bond. sp2 means there's still one p orbital, and that's for the pi bond. Hopefully you remember that from general chemistry. We're going to use this again in organic. This is still a bad structure. If you draw C's, you must draw H's. So go in and make sure carbon makes 4 bonds. Let's see, 4 bonds to this C already. Got the H's on the same side, so it's cis. Good. If you like it this way, or if you want to throw in this, if you like it that way, I'll let you mix and match. But if you have C's, you must have H's. If you want to throw in some H's, you can mix and match, but you don't have to, right? So we could have just drawn it like this. And that's cis 3-heptene also. This one happens to be trans 3-heptene. Oh, close that out. Triple bonds. The only difference here is that you change the suffix not to -ine, but to -ine. A-E-Y, alphabetical order. The alkynes have at least one triple bond. And then it's Molly eats peanut butter. You can't have a triple bond in methane. You need at least 2 carbons, so you can triple bond them together. So ethyne, where it used to be ethane, propane becomes propyne, butane becomes butyne. Triple bond can be in the middle or at the end, doesn't matter. Oh, common names. So the standard IUPAC name is ethyne, but the old name before the committee came along was acetylene. Any welders out there that use acetylene torches? Yeah, that makes a very hot flame because triple bonds have a lot of energy. So you burn this, burns with a lot of heat, good enough to make a blowtorch out of it. Acetylene. So what have we else got here? So we got names. You also number the beginning of the triple bond with a number, just like we did with the double bonds. No cis and trans, right? Because what's the hybridization of, well, let's do this one. What's hybridization of this carbon? It's got a triple bond over here that counts as one group. Single bond, there's 2 groups. Pen, please. It's got 2 groups of electrons, a triple and a single, so it needs an S and a P. It's sp hybridized. And what's the shape of sp? Linear. Yeah, so since it's linear, all the groups are going to be lying in a line. There's no cis and trans. That's good. One less thing to worry about. Hey, let's name this molecule. Okay, so find the longest chain. Well, that's nice. It's a chain of 5, no branches. What's the name of for 5? Molly eats peanut butter, and then it's pentane. It's 5 carbons if it's all single bonds, but it's not. So we're going to use Y, YNE for triple bonds. Oh, wait a minute. They got a double and a triple. Yeah, let's not name this. I don't want to contradict myself. Didn't I say earlier we're not going to have this problem? Ay, ay, ay. Not on the exam. For those of you who are curious, turns out you want a number from the end that gets you to the first multiple bond, whether it's a double or triple bond first. So they numbered it correctly. Number for this end, not here because that starts a single bond. Not so interesting as a triple. So number from this end. You now have to keep, well, you have to use an ine ending to say, hey, yes, there's a triple bond. But you also have to use an ene ending because, hey, there's also a double bond. And you have to use numbers for each of them. So the triple bond begins on carbon 1. The double bond begins on 3. And I can't tell if it's cis or trans. Trans. I can't spell. So we have to leave it out. These H's, are they on the same side of the double bond or are they on opposite sides? I don't know. Can't tell. So leave it out. And then when you name this, instead of pulling the numbers out in front, you can't do that. You have to keep the numbers next to the suffixes. Otherwise, you don't know which number goes with this, which suffix. You won't know whether the ene starts on 1 or 3 if you pull the 1 and 3 out in front. So it's kind of weird. You have to keep the numbers with the suffix, and you put it in alphabetical order. So 3 ene, and you're waiting for me to put that other E in here? Well, the committee said, well, if you didn't have the numbers, the ENE would be right up against the YNE, and they did not like having two vowels together. So they want you to drop this E, which is silly because you don't put the Y next to the E, you're gonna put the number next. Anyways, that's the name of this compound, pent 3-ene-1-ine. Not on exam. We'll save it for your full-blown organic chemistry course next time you take that class. Functional groups. We've actually seen 3 of them already. A functional group is a group that has a particular function. Oh yeah, that's a great definition. No, it's not. If you look at a molecule, usually organic molecules, anything interesting is called a functional group. It's just a set of atoms that are doing something a little bit different. And actually, even a carbon-carbon single bond, which is the most common type of feature, that's a functional group. It's called an alkane. A carbon-carbon double bond is called an alkene. A carbon-carbon triple bond is called an alkyne. And those are 3 functional groups. There are other functional groups too. Here's some examples. So we saw alkane. There's an example, all single bonds. An alkene, carbon-carbon double. Alkyne, carbon-carbon triple. If you alternate double, single, double into a ring of 6 carbons, that's called an arene or an aromatic molecule. And it's one of nature's favorites. She likes making these aromatic compounds. You might think they smell pleasant. Some do, some don't. But yeah, that's where the name comes from. The most common example is a ring of 6 and hydrogens on all those carbons. That's benzene. This is not 3 alkenes. It's weird. You can do chemical reactions on the alkene and the same reagents, like an acid. Acids react with alkenes, but an acid doesn't react with this. Weird. Wait, it looks like it has 3 double bonds. Shouldn't it react 3 times if this reacts 1 time? The answer is no. Nature makes all the rules. So it's a separate entity, a separate functional group. The alcohol in beer and wine, ooh, it's not this one. This one causes blindness. Ethanol, whoa, I did it again. I keep on doing it. The alcohol of beer and wine has 2 carbons. It's ethanol. Why is it eth? 2 carbons is ethane. And now you change the suffix. Well, you kind of keep the ane suffix, but you add an ol, ethanol, to represent an alcohol. That's supposed to be an O. But the OL, alcohol ends in OL, so we borrowed that as and used it as a new suffix to identify, hey, this 2 carbon group, ethane, has an alcohol group, an OH group. That's an alcohol group. There's an ether, oxygen with single bonds to carbon. Oh, are you worried about memorizing these? The only ones you need for the exam, the final exam in general chemistry is alkane, alkene, alkyne, alcohol, and then that's all that's on this page. We'll need the aldehyde, the ketone, and the carboxylic acid and the ester. Aldehydes and ketones, really important. They're found in carbohydrates. Glucose blood sugar has an aldehyde in it. Also has a lot of alkyl groups in it. If you've heard of high fructose corn syrup, that has a ketone in it. Carboxylic acids, you actually saw these in all those ice tables of weak acids and bases, like acetic acid. Oh, here it is right here. The molecule found in vinegar is acetic acid. The IUPAC name is ethanoic acid. So you've seen these weak acids already. That's a functional group. These 4 atoms make a functional group called the carboxylic acid. And then there's esters that are found in fatty acids, a lot of fragrances, natural scents. Now this one has a little bit of controversy, not controversy, but a little ambiguity. Sometimes students say it looks like it only has 3 atoms in the functional group, but it really has 4. You have to kind of include this carbon, because if you didn't include the carbon, if it was a hydrogen, it's not an ester. It's a carboxylic acid if it has a hydrogen. The carboxylic acid does not also have a ketone or aldehyde, right? So an aldehyde is a C double bond O with an H, and this C double bond O does not have an H, so it can't also be an aldehyde. A ketone is C double bond O attached to 2 carbons. Well, this C double bond O is connected to O, not 2 carbons. It can't be a ketone. It's only a carboxylic acid. Oh, we just saw the alcohol group, right? So the alcohol found in beer and wine had an OH group, an alcohol. So some students say, oh, this is also an alcohol group. No, it's not. Sorry. This hydrogen is released easily. That makes this a carboxylic acid group. This hydrogen doesn't come off easily. It's brand new functional group. It's a different entity. So this is not an alcohol group. It's part of 4 atoms. It's a carboxylic acid group. I tell students the functional group with the greatest number of atoms dominates, supersedes. So some students say, oh, isn't also a ketone and an alcohol? And the answer is nope. Those are smaller functional groups. The 4 atom group's the bigger one that dominates. This is only a carboxylic acid, not a combination of other functional groups. The amide group, not on the, I won't put that on the exam, but it's found in proteins. Amines, those are found in, well, you saw those as weak bases in your ice tables when you talked about weak acids and bases. Yeah. Cool. Okay, enough said about functional groups. You'll need to know the group. So if I say, hey, circle and label, so I might draw a molecule and you'll have to circle the C double bond OH and write next to it, this is an aldehyde. Or I might say, hey, draw for me a ketone. Pick a molecule and draw a ketone in the molecule. So then you have to make sure you have a double bond O, carbon-oxygen double bond, and that carbon has to be connected to 2 carbons, and then it's a ketone. You'll get more examples in the homework and on the sample test. We're just reiterating, hey, the alcohol group has an OH. Ooh, here's a common mistake students do. Sometimes they think this is a strong base. Wait, why do they think that? Because it looks like sodium hydroxide. That's got an OH group too, right? Yeah, it does. But the sodium and the oxygen are connected through an ionic bond. That means this oxygen has 3 lone pairs. That extra lone pair is what makes it so basic. Oxygen's not doing honk. it should be making 2 bonds and it's stable, but right now it's only making 1 covalent bond. It wants to go steal an H plus to make 2 covalent bonds and be more stable. This oxygen is not negatively charged, right? So carbon bonds 4 times. This oxygen is quite stable. It's got 2 covalent bonds. It's not negative. It's not a base. This is not a strong base. Anyways, it's the alcohol function group, different from hydroxide ion. Oh, alcohols can dissolve in water because the OH group can hydrogen bond, just like water hydrogen bonds. How do you name them? We actually already hinted at that. Change the suffix to OL. And that's the most interesting feature of the group so far. I won't put a molecule that has a double bond or a triple bond and an alcohol. No. So we'll just leave it, you know, number 3 carbons from the end closest to the alcohol group. This, I should have deleted this slide. Left in there just to show you some variety. Here's some molecules that have multiple alcohol groups. Ethylene glycol is used in antifreeze in your car, the radiator of your car. Glycerol, that comes out of hydrolysis of fatty acids. When you break down fats and lipids, you can make glycerol. It's also great for making soap bubbles. Propanol, here's rubbing alcohol. Propanol, propane, 3 carbons. And where's the alcohol group? It's coming off of carbon 2, the middle carbon. So 2 propanol. All right, let's name this one. So step 1, find the longest chain. So where's the long chain of carbons? Well, you can start up here and go across there to get 5, or you can just go horizontally and get 5. You get the same name. Doesn't matter which chain of 5 you pick. Picking that 5, and then name it Molly Eats Peanut Butter, and then pentane. Any double or triple bonds? Nope, then you can keep the ane ending. Is this carbon 1 of pentane, or is this carbon 1 of pentane? Yeah, this one is, right? Get to your interesting groups as fast as you can. Prioritize the suffix. We're going to name the alcohol using the suffix OL. So we're supposed to number it from this end so we can get to that alcohol as fast as we can. I guess I don't have to finish numbering the chain because there's no decorations, no branches or other functional groups down here. But I did just to be complete. Off of carbon 2 is the alcohol group. So we're going to put a 2 in front of the parent name. And then we're supposed to drop the E before the O because IUPAC doesn't want 2 vowels. If you do that accidentally on the test, you leave the E in there, I will ignore it. But you're supposed to drop it. No points lost if you forget to drop the E. Okay, so we named the alcohol group, the OH group. It's on carbon 2. We also have to identify this 1 carbon branch, moly, methyl, and it's off of 2 also. So this 2-methyl, and separate the letters from numbers with dashes. There we go, 2-methyl, 2-pentanol. Aldehydes and ketones, we've done enough naming. I won't ask you to name molecules that have aldehydes and ketones, but instead you just need to be able to identify them, right? So an aldehyde is a C double bond O with an H. Ketones is a C double bond O with 2 C's. Carbonyl is another name for it. Actually, you remember that from transition metal complex. It's a C double bond O group. The carbon monoxide group could be attached to a transition metal. And so carbon in an organic molecule could be a C double bond O group. So sometimes with their nicknames for aldehydes, ketones is a carbonyl group. I think it was a nickname. Oh, here's some blood sugar. Here's glucose on the left. And sure enough, there's the aldehyde group with lots of alcohols, 5 of them actually. There's an OH here. Testosterone, a steroid, has a ketone in it. It also has an alkene and some methyl branches and an alcohol group. Hey, there's 4 functional groups in this one molecule. It has alkanes, alkenes, a ketone, and an alcohol group. Cool. Carboxylic acids, we mentioned that before. These 4 atoms, C double bond O with an OH group. Those 4 atoms make up a carboxylic acid. They're weak acids. They lower the pH of water when they're present. And if you change the H to a C, and of course C has carbon, needs 4 bonds, so put some other groups on there, hydrogen in this case, that makes an ester. And that's all I need you to know. You're not going to name molecules with these groups in it. Is that it? More examples? Yeah, whatever. Long molecule here. This comes from a fatty acid. It's one of the simple, well, you can use this to make a simple soap. But you see C double bond O with an OH is a carboxylic acid group. There's the aromatic ring, another functional group. Interesting stuff. Yeah, maybe I should delete more slides. This is more review. The alcohol group, aldehyde group, carboxylic acid. Oh, I know why this is here. If the R group, sorry, little nickname or shortcut in organic chemistry, try to avoid using that. It means the rest of the molecule, the remainder. So someone didn't write in the rest here. If the R group is a methyl, so if the R is a methyl, then this is ethanol, the alcohol found in beer and wine. Okay, so ethanol by itself is a mild toxin, right? You get intoxicated by drinking too much beer or wine. You've heard of how it damages the liver. Well, the liver in your body is trying to remove toxins from your body. And one way it does it is it's got some powerful enzymes. Nature's catalysts are enzymes. And what it'll do, it will oxidize the alcohol in beer and wine, trying to make it more water soluble. And that, unfortunately, it's already very water soluble, but it does it anyways. Changes it to an aldehyde. It's got a methyl group on here. And if it had a hydrogen, it would be formaldehyde. Anybody work in the lab, in the biology lab with some preserved specimens? They've been preserved with formaldehyde. So in your liver, alcohol gets changed to acetaldehyde, which starts to preserve your liver and damage it. It can also oxidize that to carboxylic acid. It changes it to vinegar, and that's less toxic. And actually, it's still water soluble. It gets excreted in the urine. Anyways, that's one reason why your liver can get damaged by too much alcohol, or, what's that called? Not excessive, chronic use of alcohol can cause damage to the liver. One way is through the production of acetaldehyde, these aldehyde groups. Carboxylic acids are weak acids. Hey, they got Kas. You recognize that. Doing it again. Oh, we can do a titration on it. Sodium hydroxide, titrating this carboxylic acid. They're acids. Treat with strong base, titrate them. Esters, here's some examples. There's benzocaine, numbing agent. Aspirin relieves pain, lowers fever. It has both an ester and a carboxylic acid group in it. And the aromatic ring, 3 functional groups there. There's an amine, which we didn't talk about. Well, not in great detail. Aromatic compound, ester, 3 functional groups also. And that's it. Okay, that was plenty. But that's enough for now. I will see you in the next video.